Welcome to the Presidential Lecture Series on Clean Energy and Environmental Sustainability. Today's speaker is Dr. Ernest Moniz. This lecture series is affiliated with Boston University's Clean Energy and Environmental Sustainability Initiative, a joint initiative between engineering, College of Arts and Sciences, and the School of Management, and with a mission of designing and providing powerful education and research experiences at the interface of technology, public policy, economic and environmental sustainability, and systems, all from a systems perspective. Our initiative is synergistic also, of course, with Boston University's Sustainability Initiative dedicated to making the institution as green as possible, and with the BU Energy Club with over 600 students. The speakers from this series derive from government, academia, industry, and national laboratories. As you look around, you'll see a diverse audience from academia, industry, and government, all of which are, of course, are needed to drive the innovation in this crucial sector. After Dr. Moniz's talk, we'll have about half an hour, 20 minutes to half an hour for question and answers. Well, definitely questions. I don't know about the answers. Now, Dr. Moniz got his Bachelor's of Science summa cum laude from, are you ready for this? Boston College. All right. Which has one less national championship than Boston University. Total. But anyway, let's get serious. His doctorate is in theoretical physics from Stanford University, and he has an honorary doctorate from the University of Athens, the University of Erlangen-Nuremberg, and Michigan State University. He's been at MIT since 1973, where he is the Cecil and Ida Green Professor of Physics and Engineering Systems. He's also the director of MIT's Energy Initiative and the director of the Laboratory for Energy and the Environment. In Washington, he currently is serving on President Obama's Council of Advisors for Science and Technology. He has been the Undersecretary of the Department of Energy from 1997 to 2001, and Associate Director of Science for the Office of Science and Technology and Policy under the Executive Office of the President from 1995 to 1997. Ernie's research principal contributions are in the area of theoretical nuclear physics and in energy technologies and policy studies. He's served as the head of the Department of Physics and as the director of the Bates Linear Accelerator Center. He's a fellow of the American Association for the Advancement of Science, the Humboldt Foundation, and the American Physical Society, and he's a member of the Council on Foreign Relations. He's received the Seymour Cray HPCC Industry Recognition Award for Vision and Leadership in Advancing Scientific Simulation, and in 2008, the Grand Cross of the Order of Makarios, I may have said it wrong, I knew I'd get it wrong, for contributions to the development of research, technology, and education in Cyprus and the wider region. His talk today is titled Energy, Technology, and Policy, a Post-Copenhagen View. Please join me in welcoming Dr. Ernest Moniz.
Well, thanks, Ken, and let me say hello to Andre as well, our good friend. Pleasure to be here across the river, especially following BC's hockey championship. Right, this is very, very well timed. So, by the way, also let me encourage you. I know this seldom works, but I would be delighted to have questions during the talk. If you can just shout them out, we'll go from there. So. What I'll try to do today, and I think you had Christina Johnson, the current Energy Undersecretary, recently, and also my colleague from MIT, Melanie Kinderdine. What I will do is probably a little bit different, is give some reflections on Copenhagen, the climate negotiation process, and where, in some sense, I see at least the path forward in terms of policy and technology innovation as we grapple particularly with climate change risk mitigation in what is currently, let's be honest, a pretty uncertain policy future. As we have time, I will go into some specific technologies, but I have a dialable set of transparencies here of slides, and we'll just kind of pick them or be guided by your questions. So that'll be an incentive. Okay, the first thing is to just kind of get us on the same page. You may have seen this before. This is kind of an energy flow diagram. This was produced by Livermore National Laboratory. in which on the left you see various fuel sources going into various end uses, in some cases through the intermediate step of an energy carrier, electricity. And there are several important points here. One is, first of all, if you can read the boxes on the left, you will see that the boxes at the top are not to scale. If you put, let's say, solar to scale, you wouldn't see it, right? So when you add up the numbers, the first point, of course, is that fossil fuels make up roughly 85% of the energy mix today, and this is a projection to 2030 in which fossil fuels make up about 85% of the energy mix, actually maybe a tad more, at least in a so-called business as usual approach. The fact is, fossil fuels have been used and are used for a good reason. They're cheap and convenient. And so the transformation that we'll be talking about will have to overcome, in a certain sense, through technology and through policy, this inherent advantage of fossil fuels. Clearly, you see that in areas like transportation, it's all oil. That's, roughly speaking, the classic energy security challenge. Another important point is if you look at all that gray stuff on the upper right, that is warming the atmosphere. So that's the opportunity with efficiency in terms of greater thermal efficiency of the combustion of fossil fuels. So this kind of gives you an idea. Furthermore, we're here in the Photonic Center, so I assume people are numerate, and 680 quadrillion BTU, or roughly speaking, exajoules, is a really big number. So this is as we'll come back to, this is a really massive enterprise in many dimensions, and these are all important characteristics as we begin to talk about transforming the system as we go to a lower carbon world. To get some idea of what this means in terms of the challenge, what is it going to mean when we come to talking about CO2 reductions as needed? If we go to BAU, business as usual emissions in 2050, we'll be talking about a scale of around 70 billion tons of CO2 equivalent emissions per year. CO2 equivalent, not CO2. But as we talk about the kinds of goals set forth in Copenhagen and in various other venues, talking about a 50% reduction from today's level, we're talking about, let's call it in round numbers, 20 gigatons, which, given around 10 billion people, we're talking 2 tons per year at mid-century, and the next half century only gets harder if we want to maintain greenhouse gas concentrations at the kinds of levels thought to be prudent. So, we're talking in the end about trying to transform the system over a half century, then a century, 2 to 1 ton per person. This is an important perspective. I'm not suggesting a sensible policy would be to divide up the emissions per person, but it gives you kind of a scale, which then tells you, gives you a little bit of a history for what these international negotiations are about. So here I've chosen, not randomly, but chosen a set of countries on the top, ordered by GDP per capita, starting with the United States at almost $50,000, a bunch of industrialized countries, some emerging economies like Brazil at around 10,000. This is all purchasing power parity equivalent dollars. China is around 6,000. Then we start going into, India and the African countries, essentially vanishingly small economies. Now, with the same ordering, we come to the next line, the next graph, the CO2 emissions per capita today, and remind you to put this in that context, that reference frame of a couple of tons. The United States is an order of magnitude above. China is larger in terms of absolute emissions, which is the bottom line, but of course substantially below in terms of per capita. However, if you divide the CO2 and the GDP, what you'll see immediately is that China has about twice the carbon intensity of the United States. And India, which doesn't consider itself to be economically asymptotic, is down in that 1.3 tons per region. So it gives you an idea of what's being talked about, and the very, very different starting points, obviously, in CO2 intensity, in GDP of all these countries. Another point I'll make is, this is some work by my colleague Michael Greenstone. It's a little bit complicated to go through it, but I'll give the punchline. What it shows is a mortality rate which is normalized for the United States and for India to the 50 to 60 degree Fahrenheit range, so for each country, and then what happens in terms of mortality as you go, for example, to very, very hot weather. What you see is more poor people die. That's what this says. So the point is, as we think about this kind of international negotiation, we've got to remember what the real issues and the real stakes are. Energy services is about things like, for example, health and mortality, in addition to economy, etc. Indeed, if we look at this slightly out of date, but nevertheless good enough for our purposes, plot, which shows the average annual, the annual per capita electricity use in various countries against the UN Human Development Index. The UN Human Development Index, by definition, runs from 0 to 1, and it weights three major buckets indicating, in some sense, quality of life, education, economic performance per capita, and educational level per capita. What you see is the industrialized countries in the green dots are all up in the 0.9 plus Human Development Index, and all use anywhere from, say, 4,000 to, with Canada, 16,000 kilowatt hours per person per year. U.S. is up. This is 2,000, so this is now we're up around 14,000. But then as you come down to the left, you obviously see the crude correlation, and once again, if we use Africa in terms of the least developed area in many ways, those are the purple dots, with an exception of like South Africa as an outlier. What you see is, of course, very low human development indices and very low levels of energy services. So putting that together with the last slide, what we're talking about is moving up this trajectory. And if we do a simple physicist's Andre back-of-the-envelope calculation, let's take 10 billion people at mid-century. Let's put 1 billion people up in the, you pick it, 10,000 kilowatt hours per person per year. Let's take 8 billion people and put them up around 3,000 to 4,000 kilowatt hours per person, which is where the knee in that curve. And let's assume 1 billion have 0, reflecting kind of what appears to be a constant of history, that 1 billion people are always left behind. That's not a goal, but I'm just saying, let's put that in. You can do that arithmetic pretty easily, and what you find is that corresponds to nearly tripling electricity use by mid-century. So when we talk about these big numbers, producing a lot more energy services, all we're talking about is trying to get most people up this curve by mid-century. And now, as we know, and we'll talk more about it, and yet we've got to do that while getting those carbon numbers going down from 10s and 20 numbers to 2s. So that's the challenge. This is, in my view, this is not about being pessimistic. We're going to come to approaches, but we got to understand the technical challenge in doing this, and the human challenge, and the negotiation challenge, because countries who are there with very different perspectives than we have a very good reason to have a different perspective than we have. And this is all a very important coloring of what is generally perceived as the Copenhagen debacle, which I will also come back to. A last point in this kind of framing of how this challenge works is this is a plot, actually Steve Koonin, another physicist, put together in terms of the, if you like, the market share of different fuels in the United States over 150 years. As you can see, wood still quite dominant in 1850, coal coming in, then oil, well, hydros is kind of fixed, but then oil coming in, gas, nuclear, little tiny sliver of purple renewables, which you can barely see, up to the year 2000. The point I want to make here is simply that historically, the characteristic timescale for significant transformation of the energy system is like half a century. That's kind of the typical timescale. The message is going to be of this challenge that we are framing is that we don't have 50 years. Again, I won't go through the arithmetic, but literally it is arithmetic. If you look at the amount of carbon dioxide that we are emitting from fossil fuel combustion, if you take a credit that, roughly speaking, at least in the range that we are in today, roughly speaking, half of those emissions are net absorbed into the oceans and biosphere, and you just calculate it out, then you find that by mid-century, we are already essentially at the doubling of pre-industrial concentrations. Doubling of pre-industrial concentrations, if we could stabilize there, would not be horrible. It wouldn't be 2 degrees centigrade, most likely. It would be higher than that, but it wouldn't be horrible. But of course, that's just mid-century, and on that merry path, we would just keep going up. So the issue is, we got to change this massive system really in the next 10 to 20 years, its direction, in order to be able to get the decarbonization at the kinds of levels that we want. So, as I'll come back to, the real question is going to be, how do we accelerate significantly what you might even think of is a historical transformation towards lower carbon fuels going forward, doing that while providing the energy services to give, let's say, better human development indices to another 8 billion people. I might say, if I go back to that actually, since we're close to MIT, I will note one of my favorite stories that, MIT was founded in around 1860, 1861, and our founding president, William Barton Rogers, was the state geologist of Virginia, actually, before he became president of MIT, and invented the concept of an institute of technology in a certain sense. A sad story, perhaps, is that this is not a joke, that he died during a commencement exercise, and his last 2 words were bituminous coal. Now, you might argue that that this kind of foresight is maybe what we need today. Maybe, Andre, you can say renewables, and we can have that wedge open up, right? So anyway, that was right. Please do not act on this anyway. This was all right. So innovation is key. As I said, we have to accelerate the transformation if we are to meet prudent climate change risk mitigation goals, but also meet demand and enhance security too. I will not talk as much about energy security issues. Now, let's put this in context. We're still on the this is a hard problem part of the talk. Let's characterize the energy business. I don't think any of these nouns and adjectives should be surprising individually, but when you string them all together, it kind of gets a bit heavy. Very highly capitalized. This is a highly capital-intensive business. It's a multi-trillion-dollar per year business. It's a commodity business in the following sense. That light over there doesn't know whether the electron is coming from a super-duper great photonics center PV or from a coal plant. The new technologies, to good approximation, these great new low-carbon technologies, they're not giving you any new function. The great new biofuel, you put it in the tank like oil-based fuel, and you drive. Even a battery, frankly, mostly is about getting from point A to point B. It's true, electrification will give you some additional possibilities. We could go into that, but at the core, it's about providing heat, light, and mobility, right? That's very different from a lot of the information-based technologies, or a cell phone gave you something really new that you could do, or a Google search. Very efficient supply chains, established customer bases, obviously providing essential services. You couldn't see my slides without them. That's an essential service. And this, of course, calls for extensive regulation and, frankly, very complex politics. That is, it's kind of like, sorry, but that's the energy business. It is not exactly what you would write down as your prescription for a nimble, innovative structure. In fact, we often, have, negative views of, let's say, utility CEOs. Well, they are very reasonable people in general, in terms of doing business. Because what's their reward? Their reward is for reliability. It's not for innovation. If your lights go out, that has a much bigger impact on his quality of life or her quality of life than does going out to the shareholders and saying, gee, we just did a great little innovation in that substation. So that's just the nature of the business. So we have to innovate. We have to think about it in this context if, in fact, we are to succeed. And the implication is very clear. The goal of innovation in energy technology is cost reduction. That's what it's all about. It is cost reduction. We can go on with as many public subsidies of this and that as we wish to kickstart a new technology or whatever. But at the scale of a multi-trillion-dollar per year business, you better have economic choices being made in the end about costs. And even if we and our European brethren are willing to do otherwise, China is not willing to do otherwise, India is not willing to do otherwise, and certainly less developed countries are not willing to do otherwise. So you just got to keep this in mind. This is about novel, innovative new technologies that lower the cost, at least the cost as defined by policy, such as, for example, a price on carbon emissions. Okay? That's the game. There are some exceptions, and for example, what I called here, even though Mr. Hyundai does not know it, I think that he's been assigned a principal. Mr. Hyundai is an entrepreneur in India who's done a terrific job with small-scale photovoltaics linked to microfinance, done a lot of stuff in rural settings, et cetera. And his principle was, with regard to his business, is that photovoltaics are too expensive for the rich, but quite affordable for the poor. And it's a very wise statement in the sense that when you're dealing with people with no energy services, even though it is inherently expensive, a small module can qualitatively change a life. So it's very important. But we're talking about carbon, and we're talking about things that scale into the terawatt scale, the gigaton carbon scale. That's what we're talking about. And so it's about cost. All right. So now we need innovation. And now I will actually start to get more cheery. But we need to think about it in the context of the real problem as, at least in my view, at least in my view of the problem and the challenge as we have defined. And the first point is that innovation, we're here, I don't know, I think kind of in the School of Engineering, and at least the Dean of Engineering introduced the talk. Technology innovation is essential. Again, cost reduction the goal, but it's not enough. I will posit that we're also going to need, in a synergistic way, business model innovation, I'll explain this a bit more, and policy innovation. Again, my one tagline here on the policy innovation, what is the road from Copenhagen, and we'll talk about that, and on business model innovation, as one example I will give is that historically, one would argue that very, very large, let's say very large petroleum companies, it's similar to my statement about utility executives. They're doing what they get rewarded for. Large petroleum companies are innovative in many ways in their core business. As you know, I think almost all of them are looking at much broader portfolios, looking ahead to carbon emissions control. On the other side of the coin, we have an unprecedented amount of innovation going on in energy technologies. Businesses spinning out, MIT, many, I'm sure, out of BU, out of Harvard, and out of universities across the country. But frankly, we've never figured out, in my view, how to put those together to accelerate not only the introduction, but the scale-up of these technologies quickly. That's an example of a business model innovation that I think we need to figure out pretty soon if we're going to get the right scaling. So let me talk about Copenhagen a little bit. And I said earlier, and I want to make sure the words were heard, Copenhagen, I think I said, what is usually thought of as a debacle. I do not. I think Copenhagen was actually a significant success in a way that I will define. And I believe has provided a better chance of moving more promptly towards carbon control. And what I'm speaking about, of course, is the Copenhagen Accord, which our President Obama, essentially brokered with Brazil, China, India, South Africa, and then took to the Conference of Parties. And why do I say it's a success? Well, to be honest, first of all, it's because I have had, for a long time, no expectation of convergence of the UN process. A consensus process is very, very difficult to imagine converging when you go back, especially to that earlier graph showing the very different GDPs and CO2s, et cetera, et cetera. That's very hard to put into a treaty agreement with consensus of 192 countries. And that literally is the process that was being pursued. Now, there's a lot of criticism that the Copenhagen Accord is nothing but a political agreement versus a treaty agreement. My response is, so? In the real world, I don't think there's that much of a difference. Secondly, what it did is it put forward with a country from obviously the developed world, with the major emerging economies, especially, well, China, India, and Brazil. It put forward an explicit recognition of very, very differentiated approaches to carbon reduction. I'm not going to be Pollyannish and claim this is all great, but this is important. So very different structures of national commitments, which I'll come to. For example, the United States, at least nominally, put forward a pledge of a specific carbon target, as did Europe, whereas China, India, for example, put forward carbon intensity reduction targets. We'll come back to what that means. Very importantly, quite simply, the Kyoto Protocol reinforced I guess you could infer my views, reinforced what is too often the UN dynamic, the black and the white. Here, you got, frankly, the G77, not as a bloc, but China and India, whatever reason, joining with the United States in putting forward the structure. I believe that this is the beginning of what will hopefully be sustained, a movement towards the large emitting countries basically deciding what they're going to do. 15 to 20 countries, you're talking 80 to 90% of the CO2 emissions. You got to do that, then take it to the rest of the parties. And frankly, if the least developed countries should not be asked to be doing anything heroic at this stage. So I think a much better political structure began to emerge. Will it stick? We'll come back to that. And I think also it was a focus on action, as we'll come to, because most of the pledges put forward, and now over 100 countries have signed up with pledges. They are pledges, one way or another. They're often hedged, so again, I don't want to go overboard, but they are generally phrased in terms of domestic legislative actions that will be taken in their own context. There was a start, at least the beginning of a start of an acknowledgement by China, for example, on the need for transparency of monitoring and verification of carbon emissions. This is a big deal. This is a huge deal. I think very important, the critical role of adaptation to the effects of climate change was acknowledged, and furthermore, it was agreed that money would be put behind this, going up to $100 billion a year for the least developed countries. Indeed, Brazil pledged to provide funding for the least developed countries in this way. So, to me, this was a tremendous change of the whole, approach. Will it stick? I don't know. So I think a huge issue this year in heading to Mexico is there going to be a strong push from some in Europe, from some in the least developed countries, to put Humpty Dumpty back together again? In my view, Humpty Dumpty will never get put back together again and lead to a serious treaty. Maybe I'll be wrong, but that's my view. And to do so will just cost us more time, and we don't have time. So I think actually the EU has a particularly critical role to play in, hopefully, in my view, moving us towards an understanding where the key negotiation is among the large emitters, and then that will go and eventually, through various mechanisms, bring in other countries as we go down the road. In fact, a statement that there are various venues. The Major Economies Forum is something the United States started, and therefore it's unlikely to be the place to do this. The G20 has been talked about. It's a place to do it. And these are just maybe, these sound like just throwing out various names, et cetera. They have great consequence. For example, suppose the G20 were charged to put together the fundamental agreement. That would, in some sense, put finance ministers to the fore rather than environment ministers. So these are big deals, and there's a lot of politics in here, but I think the dynamic, at least, it got unlocked, and the question is, will it stay that way? So this is, I think, very, very important. Now, again, in terms of some of the initial registrations, the U.S. Put forward with the proviso that it depends upon congressional action, the kind of target that was in the Waxman-Markey bill, that is a 17% reduction below 2005 levels by 2020. As I said, China, on the other hand, let's just look at USA and China. China put forward a 40 to 45% lower CO2 to GDP ratio by 2020. Now, I remind you, they started out with twice the carbon intensity of the United States, so this would get them approaching the United States in carbon intensity in a decade. It's not bad. CO2 emissions will still keep going up. In fact, with their plan, they won't peak until 2035. But I think if we start on this road, I think they'll beat those targets and do better. But it's very, very different, and I think it reflects reality, and I think it's a very rational way to go. For the U.S., an interesting question is to ask, what does it take to get that 17% reduction? Is that big or small? It's big, is the answer. In fact, when you get rid of all the fluff, there's really only two major tools in our toolbox to do 17% in this decade. Renewables can expand really aggressively and do a small piece of it. Nuclear power, we'll probably have 5,000, 6,000 megawatts of new nuclear power by 2020. That's probably less than 1%. The two big tools are demand reduction, efficiency, and other ways of reducing demand, especially in buildings and transportation. And we simply have to replace the oldest, typical, often small, least efficient coal plants with natural gas. You know, sorry, but that's all there really is if we are to go to 17%. Although I don't see what's to be sorry.